Hello, my name is Dongbin Ho. Today I'm going to present our work on the very high frequency integrated voltage regulators for the portable devices, such as smartphone, tablet computer, and e-readers. The concept of integrated voltage regulator, which is called IVR, is to run the VR at very high frequency to track the processor demand and save energy. Here shows two generations of Intel's IVR for Haswell and Broadwell processor. In the first generation, the IVR is running at more than 100 MHz with air-core inductor integrated in the processor package. In the second generation, the inductor is moved out from the processor to a 3DL PCB module in the motherboard level. We propose to extend this IVR concept for small portable device applications such as smartphones, tablets, etc. Here shows the voltage regulator design in iPhone 6. There are multi-phase buck converters powering CPU, GPU, DDR, and so on in the SoC processor. You can see the passive components are occupying large amount of motherboard footprint. The output inductors are surrounding the SoC processor at top side of the motherboard, and many capacitors are surrounding the PMIC at bottom side of the motherboard. Instead, CPIS proposed to borrow the IVR concept and use a 3D stacked structure of PMIC and multi-phase integrated inductor to save the footprint. The multi-phase inductor is implemented with multiple vias in one magnetic component. Each via serves as one phase inductor, so multiple vias forms a multi-phase integrated inductor. In the design, we will abandon air-core concept. Instead, we will identify proper high-frequency magnetic materials to form the inductor core and confine the very high-frequency flux. The VR will run in tens of megahertz, and the inductor will be designed with ultra-low profile and small footprint to fit the stringent requirement of smartphone. Here shows the single-phase inductor design example. The magnetic material we use is NEC sulfide flake material. Its material property is characterized up to 40 MHz for our design. Here shows the design example at 20 MHz. The design is made with 3.8 volt input to 1 volt output with 3 amp maximum DC current level. Each line in this figure corresponding to a certain inductance value and current ripple. The blue shaded area shows the inductor size that could fit the stringent space requirement of smartphone. Each point in this figure shows an inductor size, and the corresponding loss is labeled beside it. The design example is chosen with 2 mm by 2 mm footprint and 0.5 mm in profile. After the single-phase inductor design is made, we can integrate multiple phases based on it. First, we integrate 4 phases together, and we find that the magnetic flux is concentrated in the corner, and the center space is underutilized. So then, we add the 5th phase in the center to form the 5-phase integrated inductor, and better utilize the magnetic material. This is the testing board for the 5-phase integrated inductor. The switching device is Semtex SE220. This device can provide 20 MHz switching frequency. The 5-phase integrated inductor is sit right in the middle of the board. There are 5 vias in the inductor, and each via serves as a 1-phase inductor. This is the working waveform at 20 MHz. The top waveform shows the switching node voltage. The input voltage is 3.8 volt and output voltage is 1 volt. The bottom waveform shows the inductor current shape. So although you can see this is a 5-phase integrated inductor, but the coupling between each phase is actually not strong. So almost a triangular shape waveform is shown here. This is 2-phase inductor current waveform. Because of the 5-phase interleaving, you can see there is a 72-degree phase shift between these 2 phases. That's all my presentations. Thank you.